universe was a soup of quarks and gluons called the quark-gluon plasma, and we could recreate that at the Large Hadron Collider by colliding nuclei of gold together with the machine. And we can rebuild this quark-gluon plasma when it was too hot for atomic nuclei to form, but you had this soup of massive atomic particles, subatomic particles. Then after from about up to about 3 minutes after the Big Bang, the universe continued to expand and cool, and after 3 minutes it was cool enough for atomic nuclei to form. So the quarks and the gluons stuck together into the most basic of atomic elements: hydrogen, helium, a bit of deuterium, and a bit of lithium, actually in a particular ratio, which is a prediction of the Big Bang model, which is something like 75% hydrogen, 25% helium. And that's what we see in the universe today, to a good approximation. So the constituents of the universe, mostly hydrogen and helium, was frozen in after about 3 minutes. Then expansion and cooling again. The next landmark is about 350,000 years after the Big Bang, when the universe became transparent to light for the first time. And this is where this incredible picture, this is one of the most remarkable pictures ever taken in the history of physics. This is what that shows. See, when the universe became transparent, any photons of light that were around at that time could pass through the universe unimpeded and have been journeying from that time to us to this day. That's the time actually when electrons went into orbit around the hydrogen-helium nuclei to form hydrogen and helium atoms. This is called the cosmic microwave background radiation, and so it's a picture of exactly what the universe was like 350,000 years after the Big Bang. George Smoot, who's one of the fathers of this kind of physics, said, perhaps inappropriately in this building, but he said it, and it's true, he said it's like looking into the face of God. What he meant was that you're seeing the earliest fingerprints of the creation of structure in the universe here, and it's quite remarkable. One thing is that it's about, well, you can see there, it's about 2.72 degrees above absolute zero. The red bits are hotter than the blue bits, and the difference in temperature is between 2.721 Kelvin, 2.721 degrees above absolute zero, and 2.729 Kelvin. So it's almost perfectly uniform apart from these tiny variations. These variations tell you virtually everything you need to know about the early universe. I could lecture for 10 hours about the information contained in this. Basically, you can see the seeds of galaxies here. You can see fluctuations that were slightly denser than other parts of the universe, which seeded the formation of galaxies. And actually, just one very interesting thing is if you look at it, there's some sort of characteristic size to these blobs, right? You can kind of see that they're not completely random. They're all sort of roughly the same kind of size. That corresponds to sound waves in the early universe. So when the universe was a plasma, before the electrons went into orbit around the atoms, the sound could propagate through the universe, just like sound in an organ pipe. So you can see resonances, and you can see, you can infer the way that the universe evolved from that point, just from the way that, because you can see this sound frozen in, yeah, literally resonances. It's like you can hear an organ note, and you can work out how big the organ pipe was. You can look at this and you can decompose it into its different notes, and you can learn an immense amount about the early universe. It's quite an incredible picture. Then we carry on. We carry on from that point, and after about, billion years, let's say, something like that, maybe a bit less, the first stars and galaxies formed around those density perturbations. And we can see the earliest stars to this day with the Hubble Space Telescope, which I think is quite remarkable. Stars called white dwarf stars. These are stars that are essentially long dead. So they were hot, they finished burning their fuel, their outer layers drifted off into space, and they've remained in our galaxy